Hello, everyone. This is Sung and Aki from Bloomberg, and we're here to talk about Trino and data governance on Kubernetes. A story of how we were able to deploy Trino as a service product on Kubernetes to meet the evolving requirements of data analytics and data governance within our company. So here's a high-level overview of the data environment at Bloomberg. Our teams deal with a massive scale of data, often ranging in petabyte scale of financial data spanning across the global markets. And we acquire data from a variety of different sources, like market data, news from over 125,000 different curated news sources, as well as third-party alternative data, to name a few. Our teams often also ingest real-time streaming data and analytics for market insights. And recently, there's been a growth of self-maintained data catalogs across teams, utilizing on-prem S3 compatible object storage solutions to facilitate their analytical workloads. And last but not least, there's a need to secure data discovery for AI workloads so that only authorized users and AI applications can get access to the data for specified use cases. So given these characteristics of our data environment, there was an opportunity to centralize our data analytics infrastructure with the goal of enabling our data owners to share data catalogs securely across many other teams. What you see on the screen here is an example of the data analytics pipeline that a data engineering team may manage at Bloomberg. For instance, a market data engineering team may build their data catalogs by utilizing a variety of ingestion tools like Apache Spark, Apache Flink, or even PyIceberg. And in turn, they would use a large-scale distributed processing engine to extract and transform the data into a derivative form, or simply manage a data exploration tool to enable their data quality teams or their client support teams to interactively analyze the data. So, what is Trino, and how does it help centralize the data analytics environment we have within our firm? Trino is a scalable and highly distributed processing engine that optimizes query performance through parallel processing, as well as predicate pushdowns that is very typical of a distributed processing engine. And it has a few new tricks up its sleeve as well. It also optimizes query performance by distributed caching, which allows the cluster to be able to avoid redundant S3 reads when it's repeatedly accessing the same object. Trino is also an NSI-SQL compliant engine that integrates with popular open source business intelligence tools, and a versatile engine that provides support for ad hoc analysis at interactive speeds and multi-hour batch workloads alike. So these qualities all have made Trino a data analytics tool of choice for a variety of workloads, because let's face it, the switching costs of having to learn the different quirks of multiple different data analytics tools is very much real. And that's where we come in. We're a team that provides managed Trino as a service. On our managed Trino platform, users define Trino cluster resource configurations, like the amount of memory you want to allocate into your specific Trino cluster you're requesting, the Trino catalog definitions that encapsulate the connection properties, the connection details, defining where and how the data is going to be fetched from the data sources you specify in your Trino catalog. And then the catalog access control definitions that define who can have access to what kind of data. And in return, our platform provides two core features. Firstly, our platform deploys Trino clusters matching the provided resource configurations and catalogs that the user has requested to map to. The Trino cluster is deployed with its query endpoint and monitoring UI exposed and made available to engineers, data analysts, and AI developers alike. And as the title of our presentation suggests, we provide runtime data governance by enforcing policies that match predefined access control definitions. So these personas we refer to as data owners. They go into our platform and they administer these policies, which are used by Trino as it asks policy decision questions about whether access to specific resources should be granted to a specific Trino user. When a user submits an NCSQL query onto the Trino cluster, the Trino coordinator, before it executes the query, sends the query context that includes the user, the role, the SQL statement, over to the policy decision point, which expands the SQL statement to specific policy questions mapping to a group of resources as well as the action types in order to determine if this specific user should be allowed to access those resources. So if the policy decision point approves, then the query is executed by the cluster and voila, you get the data. But if the policy decision point rejects it, Trino returns an authorization error. So why did we want to run Trino on Kubernetes? Our tenants were typically engineering teams that looked after data lake architectures for their respective business units. And you can think of these business units as different organizations within the company, like the organizations that sell news data or market data or risk data. And one of their core requirements for a managed Trino platform was that their clusters should remain unaffected when a different cluster running in a different organization is having a service disruption. And although there are existing concepts like resource groups within Trino clusters that users can use to define the amount of resources that can be allocated to a subset of users within a specific Trino cluster, our tenants' preference was for them to have isolated Trino deployments that they could fine-tune and manage with a high degree of resiliency within their business units. So the deployment management, scalability, the multi-tenant enabling network security features that come out of the box, out of Kubernetes, sorry, made it an easy choice for us to build a Trino deployment Go controller to manage our deployments. All right, but our team wasn't just tasked with building a simple Trino deployment manager. And this is because Trino enables users to make requests to access data a lot easier, which means that the risk profile of your data and analytics environment increases unless you have proper authorization in place. And within our data environment, effectively centralizing the many engineering and business teams' workloads meant enabling our data owners to be able to share their data catalogs across Trino clusters that are running on other namespaces, while still empowering them to be able to administer the policies which determine who has access to those data catalogs. And doing this in a secured manner posed a unique challenge, which was that we needed to build a centralized catalog management and policy administration mechanism to go along with the Trino deployment mechanism we're building for a multi-tenant architecture. So now I will hand it over to Aki to talk about the technical design implementation that solves this challenge in our new managed Trino platform.
Thank you, Sun. So for centralized data access policy management, an important building block is Trino's built-in access control. When a user tries to execute a query on Trino, Trino analyzes its SQL statement before executing it and asks authorization questions such as, can this user select these columns from this table? This mechanism allows us to define the access policy up to column level. So we can say, for example, this group of people should be able to access only column A and column B from this table. There are several implementations that come with upstream Trino distribution, such as a file-based one, where you can specify who can access which data in a JSON format in a Trino configuration file. We chose an OVA-based implementation because it allows us to decouple centralized policy management and its distribution from many instances of Trino clusters managed by our tenants. So OVA is an open source software that focuses on policy enforcement in a decoupled and reusable way. It accepts policy questions as JSON over HTTP or gRPC and responds in the same way. One important feature for us is its ability to fetch policies from external services in a well-defined way out of the box. The policy data is fetched this way is called bundle, and the external service that provides the bundle is called bundler. This bundler is what we will leverage in a policy distribution so that policies can be managed in a central place without being a single point of failure or a bottleneck. So based on these underlying technologies, this is what we want to achieve. In our platform, data owners on the right-hand side should be able to expose their data with granular data access policies. In Trino, data source is represented as a catalog, which is a collection of configuration properties, including database connection strings. Then, Trino service owners on the left-hand side should be able to create their Trino clusters, which can mount catalogs defined by data owners. However, the catalog mount should come with restrictions that the data owner imposes. This is where we leverage Trino OPA plugin with OPA that we walked through in the previous slides. When users send over their queries, Trino OPA plugin enforces the policy by making HTTP request to an OPA server that is co-located with the Trino clusters. OPA then makes policy decisions based on bundled data distributed from OPA bundler. On top of this, our system is responsible for making dashed arrows happen. Firstly, data owner needs to have a way to define catalog properties in our system. Secondly, there also need to be a way for them to define data access policies over the catalog they defined. Lastly, service owners need to be able to create their Trino clusters mounting the catalogs. The data owners define their catalogs as Kubernetes custom resources in our system. This is almost like a plain text configuration file, but with the ability to inject secrets. The plain text properties field is basically identical to the resulting Trino catalog properties file, but it's without sensitive information such as access credentials. Our Kubernetes controller uses secured properties fields to generate additional fields in the Trino config file without exposing the values to service owners. This separation is not mandatory, but this allows us to safely store Trino catalog definitions to log storage, for example, without worrying about sensitive information. This also makes it possible for us to let service owners discover existing catalogs directly in Kubernetes simply by executing kubectl get or using Kubernetes REST API without showing data access credentials. Now that Trino catalogs are registered in our system, data owners can define data access policies over them. To do this, data owners define another custom resource by referencing the Trino catalog by name in the spec. And these access controls are defined as a group of tables and columns for which the access can be granted together. For example, in a data catalog maintained by a news data team, if a specified set of columns in a table, if the specific columns in the table has sensitive data, those columns may be excluded from an access control so that it can be shared more broadly across many teams within the company. Given the desired grouping of resources from the data owner, our Kubernetes controller needs to configure OPA bundler so that the bundle contains policies that can be used together with users' identification. This typically involves external identity systems configuration, such as LDAP and IAM. So we chose to let the Kubernetes controller to do the work. In our implementation, the controller also generates intermediate representations to a separate policy store to optimize the computation of bundle generation. Our OPA server periodically downloads the policy bundle that contains the policy that can be used with the user identities. Then when the user sends over Trino queries with the identities such as JWT token, the Trino is able to allow or reject the query execution based on whether or not user belongs to certain user groups or roles. In the status field of the custom resource, we show generated external resources such as policies in the policy store, besides whether these external resources are correctly configured and ready to use. So far, we went through how we implemented centralized data access control by data owners. So as a little segue, let me briefly talk about how we reuse the same infrastructure for computation access control by service owners. Since Trino queries, as well as Trino UI accesses, are via HTTPS, we introduced another open source component, Envoy plugin, that allows us to authorize HTTP accesses via OPA. Then all we needed to do is to inject additional access policies into OPA for compute resources. Now the Trino service owners can manage who should be able to access their Trino clusters by configuring an external system. As computation access control is relatively simpler compared to data access control, we did not need an additional Kubernetes custom resource with the controller in this case. But if it requires more complex setup with source tracking, such as configuration spanning across multiple systems or policy representation that does not fit into well in an existing policy store, we could do the same as data access control. So lastly, we need to enable our service owners to create their Trino clusters with mounted catalogs. But the configuration of the Trino cluster can be very complex, as you can see. We need to set up bunches of resources such as Trino coordinate and worker pods, as well as ingresses and config maps. Another complication is Trino configuration files, where certain parameters sometimes need to be derived from other parameters in a consistent way. For example, the maximum memory of each query needed to be derived from container memory size. And this is done by accounting for JVM memory consumption outside of a heap and also JVM heap consumption outside of a Trino internal memory pool. So to simplify the workflow for Trino service owners, we introduced a custom resource with very limited configuration. In this example, the Trino service custom resource has a list of catalogs to be mounted, and the amount of memory that users want to allocate to their Trino clusters in our platform. Our Kubernetes controller generates fully detailed configuration from these limited parameters behind the scenes. The obvious trade-off here is between the flexibility for service owners to configure their Trino clusters in the exact way for their very specific need versus their ease of use by not needing to even think about minor details. But more importantly, we as a platform owner have more opportunity to optimize resource allocation on our end this way. For example, if we are going to introduce auto scaling of number of workers, it will be harder if our users are specifying every single details in their pods. Instead, if service owners' expectation is more centered around the functionality, such as maximum query size or latency distribution of queries, we can introduce such optimization as long as the service level is kept above the agreed upon level. Regarding the flexibility of the configuration, we can introduce additional spec fields as we collect feedbacks from service owners and define new fields in terms of the effect they produce. For example, we added a single query limit percentage field because in some cases, service owners wanted to guarantee that at least n queries can consume a consistent amount of maximum memory. They can set this to 50 if 2 queries need to have consistent maximum, or 20 if they want 5 queries. As our controller figures out details and prepares required resources, it stores statuses of these resources in the status field. The underlying Kubernetes resources are structured in a very similar way to the open source Helm chart managed in an upstream Trino project. It also shows certain configuration resulting from the internal computation for users' information. In this case, the maximum amount of memory available to each query ended up with around 32 gigabytes. When the service is ready, endpoint URLs of a query and the Trino UI will be available in the status field as well. Users can use these URLs for running Trino queries over the mounted catalogs and look up information about their queries in Trino UI. So overall, this is what we've built. Data owners can create Trino catalog custom resources so that they can share data access configurations without exposing access credentials. And they can create access control custom resources so that they control data accesses up to column level granularity over their catalogs. Then Trino service owners can create Trino service custom resources so that they instantiate their Trino cluster, which can mount Trino catalogs with a simple spec. And also they can control computer access for users. Here we make use of the same OPA authorization backend for data access control using OPA plugin, and for computation access control using OPA Envoy plugin. And now I will turn this back to Soon to review the takeaways and the future works.
All right. Thank you, Aki. Let me just recap what we talked about within our presentation. So we talked about deploying Trino in combination with Open Policy Agent on Kubernetes to deliver a distributed and secure SQL solution that applies authorization checks at runtime. We also introduced CRDs to manage Trino-specific abstractions, like the Trino catalogs, that allow us to share catalogs and mount these properties onto a Trino cluster, as well as the Trino service that takes a very simple set of inputs that are exposed for our end users to allow them to request a Trino cluster in a very simple way and deploy that cluster on top of Kubernetes, Istio, and Envoy. We also introduced CRDs that codify data catalog access definitions named access controls, which enable granular definition of access controls in a way that maps onto data catalogs and enable centralized data governance. And finally, we showcased how all of these abstractions and resources come together in a way to support a multi-tenant platform to secure ownership of resources and enable cross-tenancy sharing of data catalogs. So now we have a managed Trino as a service platform that applies authorization checks at runtimes and enables data catalog sharing across namespaces. What's next? We still have a lot of work cut out for us, and we look forward to following the recommendations of the open source Trino community by deploying a Trino gateway alongside our Trino services to enable our Trino cluster users to run queries onto a federated endpoint that can route their queries intelligently across multiple Trino clusters for use cases like supporting a query to continue running in disaster recovery or through maintenance operations. We also look forward to enhancing our resource allocation strategy by utilizing horizontal pod autoscaling in a Kubernetes fashion. And lastly, we're looking forward to extending this exact solution across other compute engines like Apache Spark and Apache Flink so that we can reuse these definitions of mounted catalogs and apply the same level of granular runtime authorization checks across all of our compute engines that we maintain on Kubernetes. All right, thank you everyone for coming to our presentation. We have time for Q&A. Q&A. Yep. Does anyone have any questions for us in the audience?
First of all, thank you. And I was wondering, how are you guys handling updates? And you mentioned Trino Gateway at the end for a little bit, but how are you handling updates and maintenance right now with like interrupting queries and stuff like that?
That's exactly right. So our expectation or our communication to our end users is that they need to have their own retry mechanisms, unfortunately. Okay. And our first take on our managed Trino platform we just launched is to support interactive use cases. So we're focusing on supporting that first. Our next item we're working on this quarter is exactly Trino Gateway so that we can support maintenance operations without disrupting the running queries.
Okay, thanks.
Hi, thank
Hello.
you for your presentation. Quick, simple question. You had the Open Policy Agent, OPA, as a central deployment, and the catalogs were embedded. Right. What are the trade-offs of having like distributed catalogs versus centralized catalogs, and what are your thoughts around it?
Could I ask you to clarify the distinction between distributed catalogs and centralized catalogs? Are you
Yeah.
talking about like a centralized management system versus having distributed management systems in different namespaces?
Yeah, if you could go back to your slide where you summed it up.
This one?
Yeah, probably just focus on catalog part. You had the catalogs embedded on each Kubernetes deployments, right? Typically, those catalogs would update over the period of time, right? So the question was more kind of around, there is philosophy of centralized catalog for entire enterprise, and then the embedded catalogs which you have for each line of business, right? So what are the trade-offs? What have you weighed on, and how are you powering it?
So, so that's exactly what we were able to design to sort of take the benefits of both, right? When you have a distributed way of allowing our tenants to define their Trino catalogs, of course, they're empowered to use the privileges that are granted within their namespaces and update the connection properties and the catalog properties as they see fit. But at the same time, in order to be able to apply the OPA authorization checks and make sure that the rightful owners are actually the ones who are updating the access control policies for those catalogs, we still needed a way to put everything in a centralized catalog management system that goes along with the policy administration system. So our solution is a combination of the two, where your definitions of the catalogs are still defined within your namespaces, but there's still a higher level that is centralized that actually pulls all this information from the separate namespaces so that there is still, let's say, a single label or a name that refers to a specific catalog that is within a specific namespace so that the right authorization checks can happen onto that catalog when it is shared onto a different user.
I see. So if I may, if the catalog is updating at like pretty brisk pace, how do you foresee that being updated onto a centralized cataloging system?
What kind of updates are you foreseeing when you mention that the catalog is being updated?
It could be about the metadata, it could be about the people associated with the metadata and so on.
You mean the connection details or the metadata within the catalog?
Metadata about the data itself, glossaries and so on, right? So I'm taking a step further here.
Okay. Not quite sure if I understand what you're asking, but the data owners that are defining the catalogs within their respective namespaces still have the ability to be able to update it. The only thing that needs to be centralized and protected so that the access control policies can still be applied are the sort of the non-negotiable connection details of the catalogs. So like where the data is being pulled from, whether that be a specific S3 location or a specific database connection string, those are the things that needs to remain protected so that they can still, the same name that is being referred across all of our platform, all of our Trino clusters can refer to the same logical entity of the catalog.
Got it. Okay. All right. Thank you.
Yeah.
Hey, thank you for the talk. It was very good. So my team is on a very similar journey, and I would be interested to hear how stable the solution is in terms of the end user experience. So I saw you using Iceberg and Trino and Kubernetes. So yeah, maybe you can share a bit.
Yeah, nice to meet you. So we are maybe in the earlier stages of our development. So we just went into GA 2 months ago, and the existing users of our platform are having a stable experience within all of our tiers. If you're asking about the specific choices of technologies like Kubernetes, Trino, and Iceberg, I think that's a combination of technology that is being celebrated across many companies when they're using it for analytical purposes. What I would say is because it is so popular and because people have sort of tried to make use of the same set of architecture for a variety of use cases for which it might not necessarily be tuned for, I think people are often running into issues with maybe their query performance because they're sort of expecting sub-second latencies of queries for a architecture that is optimized for analytical processing. That's what I would say people have been running into issues with mostly from what I can see. Were there a specific set of issues that you were thinking about when you were asking that question?
Think more about container lifecycle management. When Trino goes down, I mean, there are so many things in your tech stack that can go wrong, right?
Yeah.
So how does that work for the user? How stable is that?
Yeah. So just like we were talking about in a previous question, right? When we're invoking maintenance operations or when a data center goes down, our current architecture requires that the Trino cluster user to figure out what other cluster that is up to actually reroute their queries. But with something like Trino Gateway sitting in front and actually intelligently balancing the workloads, that is going to be a lot easier. So there are different tools we are looking to build on top of our current solution to introduce more stability to address the problems you're asking about just right now.
Yeah, super. Thank you.